This is a LPMO, lytic polysaccharide monooxygenase. LPMO plays a significant role in catalyzing the oxidative cleavage of glycosidic bonds in polysaccharide. The materials that we use to create this 3D model are aluminium foil, plastic wrap, used color paper, bottle cap, stick, and finally A4 box cover. This clearly shows that we used more than 80% of recycled material to create this 3D model.
Based on the 3D model, we have our LPMO enzyme on our left-hand side, where it is structured with different components like beta sandwich fold. This is composed of two distorted beta sheets connected with loops and helix in the core of enzyme protein. Next, we have the flat binding site, which is crucial for the reaction with polysaccharides. Then, we have the mononuclear copper active site. The copper ion in here is coordinated with two histidine residues in the active site of LPMO, and this motif is named as histidine brace. Besides, we have a alpha helix here with their number varying that connecting beta strands in the enzyme. Now I'm going to explain about the mode of action of it. This reaction requires a LPMO enzyme, a substrate, in this case we choose cellulose, an electron, and oxygen-containing co-substrate like oxygen or hydrogen peroxide based on the pathway chosen by the enzyme. The reaction starts with the activation of mononuclear copper active site of LPMO. By the adding of electron from the electron donor like polyphenolic compounds from the degradation of lignin, the copper ion is reduced from copper 2+ to copper 1+. Then, the reduced copper reacts with the oxygen molecules as the co-substrate to generate a highly reactive oxygen species, a copper 2 oxyl intermediate. Although LPMO are considered as first as monooxygenase that uses dioxygen as co-substrate, recent investigations have suggested that they could instead be considered as peroxygenase, which use hydrogen peroxide as co-substrate. This species will then react with the polysaccharide during the binding of LPMO to the substrate. An oxygen atom is inserted into the carbon-hydrogen bond at either the carbon 1 or carbon 4 position of the polysaccharide, leading to the formation of one normal and one oxidized change end. Aldonic acid will be the product at carbon 1 hydroxylation, while 4 keto sugars will be at carbon 4 hydroxylation.